So this lesson is about average rate of change. Sometimes when we say average rate of change, we use the acronym AROC. In fact, I do that quite often in calculus. The average rate of change is when you find the slope between 2 points. And when you have a line that uses 2 points, we call that a secant line. So it's the slope of the secant line compared to a tangent. If I want to remind you the tangent line, you use 1 point. What's the slope with 1 point? The only way to do that is with a limit. Secant, 2 points, we're talking y2 minus y1 over x2 minus x1. This is on algebra. So the beginning part is a review, but then we're going to do some applications to go with it. So find the average rate of change. How would I find that between 4 and 7? So I'm going to call that the AROC. And then the numerator are the y's. So to find the y's, I have to plug in 7. I need to plug in 4 and subtract them. And then the denominator is simply 7 take away 4. That's the y2 minus y1, x2 minus x1. So this is x1 and x2 if you like. You're allowed to use a calculator if you want, but you just substitute in. F at 7 is 52. F at 4 is 4. 7 take away 4 is 3. So put this together. 56 divided by 3. Or sorry, F at 4 equals 2. I'm sorry. So 54 divided by 3. And the AROC is 18. That means the average rate of change is 18 throughout that. Again, can you find the average rate of change? So the change in y over the change in x. So to find the y, we plug in 3, subtract, plug in 0, and then just the x's in the denominator. If I plug in 3, that's 1 over 5. If I plug in 0, that's 1/2 divided by 3. With common denominators, this would be 2 take away 5 over 10. So 2 take away 5. That's negative 3 over 10, common denominators, and then times the reciprocal. So the answer is the 3's divide out, and you get the answer negative 1/10. Now let's do an application of it. So the average high temperature by month in a city can be modeled by this equation, where x is the month, and x equals 1 is January. So 2 would be February and so on. Find the average rate of change in the high temperature from February to May. So that's 2 to 5. So how would I find the AROC from 2 to 5 of that? So it would be F at 5 subtract F at 2 divided by 5 take away 2. So use a calculator or Desmos. I'm not going to show you Desmos. You can easily just plug that in and you get the answer negative or 96.75. That's the average temperature in May. Plug in 2 and you get 72.6. That's the average temperature in February divided by 3. Put that all together. And the average rate of change is around 8 degrees per month. So on average, the temperature increases by 8 degrees every month from February to May. That's what we found. Now, average rate of change, its partner is instantaneous rate of change. So here comes a second definition of a derivative. So I'm going to remind you the first definition of a derivative is the slope of a tangent line. So the slope of the tangent line is a derivative. But then I said there's many definitions we use for a derivative. That's one. So here's a second definition. The second definition for derivative is what is the instantaneous rate of change? Now, what does the word instantaneous mean? It means right now, instantaneous. It's not 2 points, but just 1 point in time. Right now, what is it? That idea. And because there's no change in time, instantaneous, no change in time, it becomes indeterminate, becomes a limit, and that's what it is when it's a derivative. And so we are finding the slope of a tangent line. So when we find the slope of this line, that is the derivative. That is called instantaneous rate of change, using 1 point, no change in time. So this is what we use, though when we do have a chance to use shortcuts, we are going to use shortcuts. So 4, using example number 3, can you find the instantaneous rate of change? Well, the instantaneous rate of change in September. So not even a change in month, just right in September, what's the instantaneous rate of change? So first I'm going to find the derivative. So if I remember the power rule, it's going to be 2 times negative 0.85. That's negative 1.7. Then subtract 1 to the exponent. Then 14x, again going all the way back here, the derivative of 14x is 14. And then the derivative of 48 is 0. So there's the derivative. Then for September, well, we know that's the 9th month. So we're going to plug in 9, and then it will tell me the instantaneous rate of change. And notice for September, the temperature, why do we have a negative? Because the temperature from August to September is going down. So the instantaneous rate of change is the temperature changes by -1 or goes down 1 degree per month at that time. So how many points is instantaneous rate of change? 1 point slope. For average rate of change, 2 points slope. Algebra. Let me move this up. Instantaneous, not algebra. Calculus. So, algebra. Calculus. That's what we're doing. Okay, the average number of people waiting in line for a ride each hour at the amusement park can be represented by this equation. Find the instantaneous rate of change. That's the IROC. So what is the derivative using the power rule? So 3 times -5 is -15x squared. 2 times 8 is 16x. Subtract 1 to the exponent. 150x is just 150. And then the derivative of -8, that's 0. Then it says find the instantaneous rate in the 3rd hour. So that means we plug in 3 instances. Wherever there's an x, plug in 3. Use a calculator. This is not about, hey, can you just plug it in and press enter? I'll give you the answer. And the answer here, if you plug in 3 and do your work, press enter with the calculator, you get 63. But we have a rate. Whenever we have a derivative, we have a rate. What does that mean? There are 2 units. So what does x represent? So if you read carefully, the average number of people waiting in line. So x represents people, and the function represents hours. So this is 63 people per hour. That's the rate. So what's the rate of change in the 3rd hour? So in the 3rd hour, we are increasing by 63 people instantaneously, not using 2 points but 1 point. Calculus. Turn the page. Same idea here. Average velocity. This is algebra. Compared to instantaneous velocity, which will be calculus. So velocity is the change in distance over the change in time. So here it is, right? And this is simply the slope, y2 minus y1, x2 minus x1. How many points do we use to find average velocity? 2. This is algebra, just finding the slope. A coin is dropped from the top of a building. The equation's here. To find the height, and t is in seconds, and h is in feet. Find the average velocity between the 1st and 4th second. So to find the average velocity, we go the change in y. So I'm going to plug in 4, subtract, plug in 1, and then 4 subtract 1 is the denominator. Now do the work. So plug in 4 into this equation, and you get 244. Plug in 1, and you get 484 divided by 3. So the answer is going to be negative, which makes sense because it's falling. So what's the average rate of change? Well, it's falling at a rate of 80 feet per second on average. That's what that negative means, falling. How about number 7? A golf ball is hit towards the tee from 75 feet away. The distance the ball has traveled at t seconds is given by that equation. Find the average velocity. That's algebra. That's AROC. The average velocity, the change in y over the change in x. So what is the change in distance? So plug in. So between 0 and 2. So we're going to plug in 2, subtract, plug in 0, and then 2 take away 0. There's the slope formula. So when you plug in 2, you get 40. When you plug in 0, you get 0. and then 2 take away 0 is 2. So divide it out and you get 20. We need a unit. It is a rate, 20 what? And so we see it's 20 feet per second. So the average velocity of that golf ball is 20 feet per second. Now, calculus is down here. Instantaneous rate of change. That is calculus, not algebra. So if the distance of an object travels, and we want to know the instantaneous velocity, so not in a change in time, but exactly at 1 second, or exactly at 2 seconds, where there's no change in time, we need to do this as a limit. This is the derivative. And if we're not told otherwise, we are going to use derivative shortcuts. So using example number 6, write an equation for the instantaneous velocity of it, and then find it at 2 seconds. So the derivative for example number 6 of the coin, so go back to number 6 and do the derivative. So that's 2 times negative 16. That's negative 32t. And the derivative of 500 is 0. So it's just negative 32t. That's the velocity. We could also write it with v. Oops, this should be a t. We could also write down often v for standing for velocity, and understanding that the position of the golf ball, you take the derivative of the position and you get the velocity. All right, next, plug in at exactly 2 seconds what's the velocity of the ball, and you can see the velocity of the coin, and it's negative 64 feet per second. So exactly at 2 seconds, that's the rate the coin is falling at. And the negative means it's falling, it's losing height. Number 9, using example 7, write an equation of the IROC of the golf ball at t seconds. So we know it's the derivative there. And if I look at the equation, it would be 2 times negative 2. That's negative 4t. And then the derivative of 24t is just 24. We could also say that's the velocity and use the letter v for that. That's common. And then what's the velocity at 4 seconds? Well, we plug in 4 and get our answer. So the velocity at 4 seconds is 8 feet per second. So exactly 4 seconds after you hit the golf ball's traveling at a rate of 8 feet per second, exactly at 4 seconds. Calculus. 10. The distance in miles that a runner has traveled at a time t hours during a marathon can be modeled by that. Find the instantaneous velocity. That's the key word to know it's calculus. In the second hour of the marathon, and t represents hours. So first, the distance or position, we need to take the derivative of that. So 2 times negative 1.7, that's negative 3.4t. And then 13t, the derivative is just 13. So there's the derivative. The second hour means we plug in 2. You can use a calculator if you want, but the answer is 6.2. And the distance is in miles. And the time is in hours. So actually this is speed in terms of, or velocity in terms of miles per hour. So exactly 2 hours in, what speed is the runner going at? And the answer is just over 6 miles per hour. All right, there's your lesson. Mr. G Math over and out. I'm proud of you that you're doing your work. I hope that you found this simpler. I think it was, but still very practical. I want you to remember the lesson. AROC, average rate of change, algebra. It's just a slope formula using 2 points. Calculus, instantaneous rate of change. That's slope with 1 point. That's a limit, but then we can use shortcuts to find the derivative and apply it. All right, until next time, I'm proud of you.